Today, I'll be talking about recombination in solids. Recombination is the reverse process to optical absorption, which I have already discussed. And one can say that recombination occurs when carriers in a solid, say electrons in the conduction band, recombine with holes in the valence band, and the energy is emitted as light. However, recombination need not be radiative. Recombination can in general be radiative, which is resulting in light emission, or non-radiative. In this case, as we'll see, the energy is given to phonons or lattice vibrations, which just results in heating of the sample. We shall now be concerned with radiative transitions. If the radiative transition occurs in the visible, it is known as luminescence. Luminescence is what occurs when light is emitted in the visible, when the wavelength of the light is typically between 300 to 650 nanometers, going from the UV to the red. Now, luminescence is a very well-known phenomena that has been studied over the ages. In fact, there are various types of luminescence which we can categorize. There are luminescence occurring due to cathode rays, which is called cathodoluminescence. Cathode rays or electron beams. In fact, this was how the first experiments after the discovery of the electron were conducted. Then there is luminescence due to radioactive particles, which is called radioluminescence. It is due to alpha, beta, or gamma rays. When X-rays were first discovered, radioluminescence was often used to detect its presence. Then there is luminescence due to light or photons, which create the electron-hole pairs, and this is called photoluminescence. These are the most common types of luminescence. However, in devices, we are interested in radiation due to electric fields, which is called electroluminescence. There's a special type of electroluminescence which is called injection electroluminescence, which is due to electric currents, the injection of light, a current through a sample. The less common types of luminescence are due to mechanical forces which is called triboluminescence. Then there is luminescence due to chemical reactions, which is called chemiluminescence. Due to biological reactions, it's called bioluminescence. And finally, there is candoluminescence, which is due to gas flames. So this, in a nutshell, summarizes the types of luminescence observed from solids. We'll be discussing entirely luminescence due to solids, in particular semiconductors and insulators. We shall not be discussing luminescence in gases or in liquids. Of these, we'll mostly be concerned with photoluminescence, and in semiconductor devices, we'll be concerned with electroluminescence. To complete the picture, there will be a discussion of different methods of stimulation of luminescence, which can be due to heat, which is called thermoluminescence. In this case, the excitation may be by any of the mechanisms given before, either cathode rays or X-rays or photons, which is followed by stimulation, thermal stimulation, which excites the electrons from metastable energy states to give rise to visible luminescence. Now, luminescence is a general phenomena which was historically divided into fluorescence and phosphorescence. The distinction is quite simple. Fluorescence occurs when the decay time of the luminescence after the cessation of the excitation is typically less than 10 to the power minus 8 seconds. And phosphorescence is said to occur when the decay time tau is greater than 10 to the power minus 8 seconds. These are rather loose definitions which divide the same phenomena. In fluorescence, the decay is often exponential, whereas in the case of phosphorescence, it could be non-exponential. We'll be going into the details of the processes at a later stage. Luminescence is a very useful phenomena, and it is seen in a wide variety of solids. For example, it can occur in insulators, such as the alkali halides. It can occur in alkali halides such as potassium chloride, which is doped with thallium. These are non-photoconducting. That means when excitation is directed at the solid, the material does not simultaneously show photoconduction. Whereas in the second case, we have materials which are semiconductors. A very well-known example, historically one of the first to be discovered, is zinc sulfide doped with copper. And these simultaneously show photoconduction. In both these cases, notice that there are impurities which are involved, say thallium in the case of potassium chloride and copper in the case of zinc sulfide. The reason the first type of material does not show photoconduction is that the material being an insulator, the band gap is very large, and excitation typically occurs from the ground level to an excited state, and the emission may occur from another excited state, which is a discrete state, giving rise to energy h nu. So this is a typical mechanism in the case of an insulator. Notice that the electron is not excited into the conduction band, which is at a very high energy. Whereas in the case of a semiconductor, we can have excitation, say due to incoming light, which excites an electron from the valence band into the conduction band, and when recombination takes place, we get light emission. So after excitation, when the electron is in the conduction band and the hole is in the valence band, there is an increase in conductivity. So this is a photoconducting type of luminescent material. These insulators are also sometimes known as phosphors, which give rise to phosphorescence, hence the name. This is one way of classifying luminescent materials. Another way of classifying luminescent materials is by distinguishing between luminescence due to impurities such as thallium in KCl, or copper, or silver, or manganese in zinc sulfide. These are impurity activated luminescence, and one can get luminescence due to the perfect crystals themselves, without any impurities, as in the case of semiconductors where you have direct band-to-band transitions. Another example, say, is in gallium arsenide. Another example is materials like uranyl nitrate, which in its pure form gives rise to luminescence. Now, before discussing luminescence in greater detail, let us just mention a little bit about non-radiative recombination, which I have alluded to before. In this case, one can have luminescence quenched due to multi-phonon emission, that means if you have in a semiconductor the electrons and holes recombining through a defect level in the trap, and this energy, excess energy, is emitted in the form of lattice vibrations of phonons. As you know, the energy of a phonon is typically only 20 to 50 milli-electron volts, and hence a large number of phonons are involved in dissipating the energy in going from the conduction band to the valence band. This finally results in heat, and finally leads to lattice vibrations picking up the energy. The other process is an Auger transition, in which when an electron recombines with a hole, the excess energy is given to a third electron, which is excited, and this loses its energy ultimately by phonon emission again. So in this case, there is no, in both these cases, there is no light emission, but instead the energy is conveyed directly to phonons, lattice vibrations in one case, and in the other case, the excess energy is given to another carrier, either an electron or a hole, and finally dissipated as in the case of phonon emission. There are many cases of Auger transitions, and if we want to have a good luminescent material, we must suppress both multiphonon emission and Auger transitions. In the case of semiconductor lasers, it will be seen how this is done by the use of strain or the use of band structure engineering. Now, let us come to a little analysis of the process of recombination using a band-to-band process. Now, as I've already mentioned, the process of recombination is the opposite of the process of absorption, and it's found from thermodynamics that is a material which is a good absorber is also a good emitter. So if we have electrons and holes created due to some excitation process, the probability of their recombination obviously depends upon the number of electrons in the conduction band, number of holes in the valence band, and there is a coefficient of recombination, radiative recombination, which I'll call Br. So the rate of spontaneous recombination is determined by RSP is equal to Br n into P, where n and P are the concentrations of electrons and holes in the conduction and valence bands respectively, and Br is the coefficient of radiative recombination in centimeters cubed per second. Now, suppose we have excitation due to photons, which causes optical absorption, then the number of electrons in the conduction band is no longer n, but it's n plus delta n, and the number of holes in the valence band is no longer p, but it's p plus delta p, where delta n and delta p are the excess carriers created. Under this excitation, we have a non-equilibrium process, and under these conditions, we have the rate of spontaneous emission RSP is equal to Br n plus delta n and P plus into P plus delta P, where let us say that in equilibrium n is equal to n0 and P is equal to P0. And we have assumed that delta n is equal to delta P. In thermal equilibrium, when there is no excess carriers, then obviously we have RSP0 is equal to Br N0 into P0. With excess carriers, we can define a lifetime which is given by R spontaneous with excess carriers is equal to delta n by tau radiative. So in other words, you can say that tau radiative is delta n by the rate of decay. So when we have both these processes operating, the total recombination rate RSP is equal to RSP 0 plus RSP excess. Now, we have already written the expressions for RSP 0 and RSP excess, so we can expand the expression and write RSP is equal to BR N0 P0 plus delta N N0 plus P0 plus delta N squared. But we know that RSP 0 is BR N0 into P0, so the first term is just RSP 0. So hence we can write that RSP excess is nothing but B into delta N N0 plus P0 plus delta N, these second and third terms. Therefore, we have tau R is equal to delta N by B delta N over N0 plus P0 plus delta N. Just using this expression, and since this cancels, this is just equal to 1 by, and we can write this B for radiative recombination as BR, say. So tau R is 1 by BR N0 plus P0 plus delta N, where we've assumed that delta N is equal to delta P. So we see that the radiative lifetime is inversely proportional to BR. Obviously, the higher the BR, smaller the lifetime. The inverse, this is BR is the radiative recombination rate. So if the rate is high, then the lifetime is small. And it is also inversely proportional to N0 plus P0 plus delta N, the total number of carriers under the excited state. Now, we can have different conditions depending upon whether the excess carriers delta N are large or small compared with the background carriers. N0 and P0 are the electron and hole concentrations without excitation. So we can have one case in which we have delta N is much greater than N0 and P0, which is the case of high injection. Because the injected carriers, as in a PN junction, the excess carriers are much larger than N0 plus P0. So obviously in this case, tau R is just equal to 1 by BR delta N. This is valid for delta N's less than or equal to 10 to the power 18 per centimeter cubed. And notice in this case, tau R is inversely proportional to delta N. So the lifetime, radiative lifetime, depends upon delta N, the excess carriers. And this is known as a bimolecular mechanism. We have the second case, low injection condition, for which delta n is less than, which is much less than n0 p0. So it can be neglected. So in this case, tau r is equal to 1 by br n0 plus p0. And notice that this is independent of delta n, unlike the previous case. So this is a constant dependent only upon br and n0 plus p0. We can have a special case for intrinsic semiconductors when n is equal to P is equal to Ni, N0 is equal to P0 is equal to Ni. So in this case, tau r is simply 2 by Br Ni. This is the case of lower injection when delta n is much less than N0 P0. Now, a word about Br, the radiative recombination rate, Br. We'll see this depends very strongly upon the nature of the semiconductor. And as we saw when we were discussing absorption processes, we have two types of semiconductors, direct and indirect. When we have direct gap semiconductor, we have very strong absorption because it's a two-body process. The electrons and holes have the same momentum. Whereas for the indirect gap semiconductor, the absorption is weak. So the reverse process, luminescence, is obviously going to be very strong in direct gap semiconductors, whereas it's going to be weak in indirect gap semiconductors. This will follow from the value of Br itself, as we'll see, for direct and indirect band gap semiconductors. Let us take first two indirect gap semiconductors, say germanium. We know the band gap in electron volts is 0.67 at room temperature. Ni is about 2.4 10 to the power 13 per centimeter cubed. For germanium, Br turns out to be, in units of 10 to the power minus 12, 0.034. And Ti, the lifetime, radiative lifetime for an intrinsic germanium is 0.61 seconds. And if we take a semiconductor doped N-type with 10 to the power 17 per centimeter cubed, then this lifetime can be of the order of 150 microseconds. Take the case of silicon, band gap 1.1 eV, carrier concentration 1.6 10 to the power 10. For this, the radiative recombination rate is even smaller. It's only 0.002. And tau I is 4.6 hours. And tau for given doping concentration is 2,500 microseconds. So we see that since Br is very small, 0.002 into 10 to the power minus 12, silicon is going to be a very weak emitter. Germanium is a little better, but nevertheless, germanium is also not a very good emitter. If you compare this with materials like gallium antimonide, which is a direct bandgap semiconductor with a bandgap of 0.7, 4.3 10 to the power 12 is the carrier concentration, intrinsic carrier concentration. Br is in the same units 13, and the lifetime tau I is 0.009 seconds, and tau is 0.37 microseconds into 10 to the power minus 6. Take another direct gap semiconductor, indium antimonide, band gap 0.17 eV at room temperature, Ni 2 10 to the power 16 per centimeter cubed. Br is even larger, it's 40. So you see that there is about 4 orders of magnitude difference between material like indium antimonide and germanium. Here, the value of tau I is about 0.026 seconds, and this is about 0.12 microseconds. So in general, one can say that for these are obviously direct gap semiconductors, and these are indirect gap semiconductors. So one can say that for direct gap semiconductors, Br is in the range 10 to the power minus 11 to minus 10 to the power minus 9 centimeters cube per second. For an indirect gap semiconductor, Br is between, say, 10 to the power minus 15 to 10 to the power minus 13 centimeters cube per second. So there is a difference of about 10 to the power 4 in the value of Br, and consequently of tau also. Now, if you want to explain this physically, one can say that for a direct gap semiconductor, if you draw the EK diagram, excitation results in the creation of electrons and holes, followed by recombination. The electrons may thermalize to a lower energy, and we'll get recombination. And since the electrons and holes have the same overall momentum, there is high probability of recombination. However, in the case of this is for a direct gap semiconductor, for a case of an indirect gap semiconductor, where we have the lowest minimum away from k equal to 0, electrons exist in the lowest conduction band minimum, holes are in the highest valence band maximum, and hence there is a process of momentum conservation required, which results in a two-stage process where this energy is given way as phonons and followed by recombination, which gives rise to the energy EPH of the photon. So in this case, if Eg is the band gap, we have EPH, the photon emitted has an energy Eg minus EP, where EP is the phonon energy. So this is just the reverse of the optical absorption process that we had seen earlier. And since this is a three-body process involving the electron, the hole, as well as the phonon, this is much less probable than the recombination process in an indirect gap semiconductor.
Sir, why PR increase with decrease of Eg?
The question was why BR increases with decrease of Eg. A quantum mechanical treatment shows that it is to do with the overlap of the electron and the hole wave functions. That if the band gap is narrower, there is more overlap between the electron and the wave functions and the respective bands, and so the probability is higher. Okay. That is for BR itself, but notice that yes, notice that BR itself, yes, there is a increase as you go to lower band gap. But then notice that Ni also increases. Okay, Ni also increases obviously as you go for, and hence the tau I is also affected by that. Tau I is equal to 1 by twice Br Ni, so it is both Br and Ni which affects tau I. Yes, any other question?
When the band gap decreases,
yes,
the excitation carrier to the higher state increases. That's why when the absorption increases, more the absorption, more will the recombination. That's why BR increases.
No, the question was that is it due to does BR increase due to the increase in absorption? No, but we are considering same number of photons incident. Okay, same number of BR is for the same number of electron hole pairs, right? So we take absorption at say the absorption edge of each semiconductor, right? So same number. We are not taking a larger number of. Notice that BR is independent of Ni and Eg. Okay, BR is in tau depends upon BR as well as Ni, right? So it is not merely due to the lower band gap. Okay, what you are saying is that if you have a lower band gap, okay, then the optical absorption increases. Okay. Right. Now let us try and combine what we've seen for both radiative and non-radiative recombinations. We have radiative recombination, which gives rise to luminescence, and non-radiative, which gives rise to heat. And so the excess carriers can decay either radiatively or non-radiatively. So we can define an overall lifetime 1 by tau, which is equal to 1 by tau radiative plus 1 by tau non-radiative. And in this case, whichever is the smaller of these prevails, because the total rate, which is inversely proportional to tau, is R plus R NR, which is the spontaneous radiation rate. Now, if you are interested in making devices, if you want to have radiative recombination prevail over non-radiative, we can define an internal quantum efficiency, which is eta R, which is R radiative over R radiative plus R non-radiative. Now, using these expressions, one can then show that for exponential decay process, eta R is just 1 over tau R over tau NR. Okay. So for high radiative recombination efficiency, this denominator should be small that means tau R should be much smaller than tau NR. For example, tau R could be something of the order of nanoseconds, whereas tau NR we would like it to be of the order of 10 nanoseconds or higher in order to. So the faster process, the rate process which is faster prevails, and then we have this denominator term small and this radiative recombination efficiency is high. For exponential decay process, we can approximate, for example, tau R by just delta N by RR and tau NR by delta N by RNR, which we have used for getting this expression. And hence we can say that if we want high luminescent efficiency, we would like tau R to be small, tau NR to be large. Unfortunately, as we have seen, for materials like germanium and silicon, we have tau R is quite large, so tau NR prevails, whereas for materials like indium arsenide, indium antimonide, and gallium, tau R is small compared with tau NR, and hence we have high luminescence. These are direct gap semiconductors, and these are indirect gap semiconductors.